I'm Wesley Harris, along with Professor Board, Professor Henry. We are the committee members guiding, supporting, advancing Stewart Isaacs to this point in his career. We also have on the committee Ben Vigorish and Olga Karaskinova, which I probably screwed up, but these are the five of us that have been partners in crime that ethics to this point. So, as the chair of the committee and the department representative for this PhD defense, I'm pleased to welcome you to the defense. Usually start by sharing a few comments about the candidate. Our friend and colleague, Stewart Isaacs. He was born in Cincinnati, Ohio, I believe, around 1907. You can see he aged very, very well. Stewart Isaacs came to MIT from Stanford University of California. He started with us in 2017. He has been an outstanding citizen, scholar, leader, thinker, creator, push, shove, and all of that advance us into advance MIT. We think he's made a substantial contribution to our intellect, to our humanities, in this changing with us. I'm pleased to offer you that Stewart was a Martin Fellowship holder, the Hugh Hampton Young Fellowship holder, a Stewart Foundation Pre-Doctoral Fellowship, and received several awards for his activity here at MIT. He has had boots on the ground and Belt in Central Africa. He's had boots on the ground building micro electric power systems. He has actually built the same, which he will talk about this morning. These are champions with him along the way, and I'm very pleased to identify Professor Wood as one of those. And my view is still in clarity. And I think that will be reflected in this presentation this morning. It's actually in the Microsoft Research Laboratory. Very high-speed stuff with about high temperatures and ionized gases and things of that sort. But this young man, this young scholar, wasn't disturbed by that. He kept focused on what he wanted to do. He did it very well. So I'm pleased to ask my colleague, Stewart Isaacs, to come forward this presentation. Desert dust solar panels, quantifying and mitigating dust impacts on photovoltaics in West Africa. Stewart?
Wonderful introduction, Professor Harris. We want to get into my presentation, a few housekeeping notes. This room is mic'd up, so itty-bitty sound can get picked up on the mic fairly well, so just keep that in mind as we progress the presentation. Other than that, let's do it. All right. So as Professor Harris mentioned, I will be presenting on desert dust and solar panels, quantifying and mitigating dust impacts on photovoltaics in West Africa. I'm joined by my committee members, Professor Wesley Harris, who is the committee chair, Professor Danielle Wood, and newly appointed in Aeronauts and Astronauts in the Media Lab, as well as Professor Ashley Henry, who is in the Mechanical Engineering Department. We're also joined by our leaders, Dr. Olga Kashnikova, research scientist and Nancy Yale, as well as Dr. Benjamin Figgis, a researcher at Murdoch University. Great. So today I will be discussing All right, first we're going to start by going over the motivation. We'll get into the background that's going to allow us to really understand the content of the presentation. But then I'll get into the meat of it, quantifying these dust impacts, mitigating these dust impacts before we finally conclude at the end. So let's do this. This project really started as a undergraduate project work that I was working on. Started as an undergraduate at Stanford University, where I met Dr. Dina Montague, who pitched this idea of developing a solar-powered poultry egg incubator, where the goal was to design these locally manufacturable incubators that use solar energy to support the food production and self-determination of a rural town outside of the capital city in Burkina Faso. So for those of you who aren't familiar with where Burkina Faso is, it's right here on the map in West Africa. You can see it's north of Ghana, to the west of Niger. And at the time that we were doing the project, Burkina Faso in the rural areas had less than 5% of the population that had access to electricity. So we were really inspired by our community partner, Marina Cabre, who was influenced by the notable leader, Thomas Sankara, who preached about self-determination and having Burkina Faso be able to feed itself. And I've been looking for ways to support Black communities with my engineering skills. As an undergraduate, I was looking for ways to support the community that I came from that I knew had quite a bit of need, not only in the US, but also abroad. And so when I met Dr. Dina Montague and I saw that this was a project I could work on, I jumped at it because I knew it would be really important for me. So since beginning that, I've been committed to seeing it through. We built a prototype, we shipped it to Burkina Faso, and there we noticed that it was not working. So then we went back to Burkina Faso. This is after I started here at MIT. This is January 2018. And once again, we could not get to work. One of the primary reasons was because we noticed we weren't generating enough energy. And so I took a lot of pictures while I was there. Here's a picture I took of the solar panel system behind a hospital that was covered in dust. And as I reflected on my journey in Burkina Faso after returning, I began to ask myself, could desert dust be having a significant impact on solar panels in West Africa? If you give me a moment, once you have to click this, okay, but not. I'm going to send you with it. Are y'all good with that? All right, very good. Let's do this. So, I've done my graduate studies here at MIT. I was actually working on a different project at the time. But I kept coming back to this question of what is it going to take to be able to get these incubators working and operating while in Burkina Faso. And so that led me to ultimately actually step away from my program after my master's and move to the region to Ashesi University in Ghana to really understand and learn more about what it's going to take to get these systems working in the context. So during that time, I actually experienced living through what's known as the Harmattan season. So you can see that on the chart to the right. This is an image of Lagos, Nigeria. During the Harmattan season, you can see that it's quite hazy. That has to do with the amount of dust that is actually suspended in the atmosphere. So when we talk about that from the climatic scale, what this looks like on the left is, I want to draw your attention to this green section. That's the intertropical convergence zone, also known as the ITCZ. And the shifting location determines the seasons in this region. So what you can see here is that when it's near the Gulf of Guinea, what's happening is that dry, dust-laden air from the Sahara Desert is blowing into the region, being suspended in the atmosphere, and then eventually collecting on the panels. Then what happens is, as the Earth continues to rotate around the sun, the ITCZ shifts northward towards the Sahara Desert. You get this blue, which is actually the rain belt. So the rains come, you get the monsoon season, the rains washes the dust away out of the atmosphere and also off of the surface of the panels. And then once again in November, cycle starts again, and you get the Harmattan season. So we expect those seasons between November and March each year. So this poses a unique challenge to solar systems in West Africa, but it's not the only challenge. One of the other challenges is related to how we actually implement these solar systems in the region. So this is an example of a project I worked on with MIT's D Lab. We're developing solar-powered evaporative cooling chambers to keep vegetables and fruits from spoiling due to the environment and the heat. And so what you notice here is that this is what I call decentralized system. It's not connected to a grid. It's not part of a solar farm. It's operating individually and has a unique set of requirements. You can see that these are actually quite commonly used throughout the region. This is an image I took on Shape University's campus. You can see that there's solar panels on the rooftops. This is another image I got from colleagues working in Lagos, Nigeria. You can see not only are these solar panels on this rooftop here, but they've also collected quite a bit of dust, which we will return to And additionally, you can see these images here. This image I took on a roadside in Accra, Ghana, where you can see these solar panels installed on top of these towers. Not entirely sure what they're powering, but we know that you see them everywhere. The same is true in other parts of the planet as well, where we see this example in Zimbabwe of these solar powered street lamps. Now, in general, as I mentioned, these are going to have very different requirements than centralized systems, which might be more common in the global north, for example. So on the left, we can look at what's more like a solar farm that you might be familiar with. The capacities are much bigger. We're talking on the megawatt scale. And additionally, the way these projects work is that they're typically financed by investors who are looking to get 25 or 30-year returns in energy sales on an energy market. In contrast, these decentralized systems, like the one I'm working on with MIT's G-Lab, oftentimes are much smaller, sometimes as small as 10 watts just to keep a light on. And many times the objective is actually system reliability. Can we make sure that these crews don't spoil in this environment? That's going to be important. We're going to come back to that. So these decentralized systems are being used to improve electricity access, especially in this region. As you might know, almost 1 billion people still lack access to electricity globally, and most people without this electricity access are living in rural areas. So decentralized PV is one way that we can begin to get energy to people without the expensive costs of establishing grid lines that go from major cities all the way to these rural areas. And so this is another project I've worked on. I've worked with the team in Tamale, Ghana. We installed these solar panels on top of this mosque to keep the lights on, as well as power from speaker systems. This picture was taken in July 2023 when I was there, right after we got it installed. This picture was taken in January 2024. So you can imagine that this dust that's collected on the surface of the panel is going to have quite a bit of an impact. Now, the easiest, clearest thing you can do is get up there and clean the panels off. But I want to also show you this picture of when we're actually installing it. If you look closely, you can actually see that these are two wooden ladders that have been nailed together. And this is actually a tin roof, which isn't the most sturdy, and so it can be quite dangerous. Even in the United States, according to the U.S. Bureau of Labor Statistics, right now we're looking at a chart of fatal work injury rates per 100,000 workers. These are some of the most dangerous jobs you can do in the U.S. You can see that logging is particularly dangerous, but roofers is right up there at number 2. So setting people up to clean the panels, sure, you can do it, but there can potentially be quite a bit of risk involved if you were to do this. So all these experiences came together to try and answer this question of could dust be having a significant impact on these panels in West Africa. My hypothesis is yes, they are having significant impacts, and that these effects can be effectively mitigated. So with that, we will get into the background where I will explain some of the things we need to know to be able to get into the meat of it in the next couple of chapters. All right, here we go. So we're going to be using some key terms. One are aerosols. This refers to small floating particles in the atmosphere, and in particular, we're going to be talking about aerosol absolute depth, which is the measure of the total amount of aerosols from the surface to the top of the atmosphere. Additionally, we're going to be talking about particulate matter concentration. This is an amount of particles by mass per unit volume, and this really refers to the amount of aerosols under the surface as opposed to in the entire atmosphere column. In particular, I want to make sure we understand those different sizes. You might have heard the term PM2.5 or PM10. This refers to the aerodynamic diameter of the particulates in the atmosphere. And then also their origin really matters here. They can sometimes have a natural origin. We're referring to mineral dust from the Sahara Desert, for example, or anthropogenic, which are generated by human activities like running your car, burning trash, etc. And so this is an example of dust soiling, which is another term I'll be using quite frequently. This refers to the dust that settles onto the surface of the panels. This is going to reduce power output. We can quantify that by using the soiling ratio. This is number between 0 and 1. 1 means you have a perfectly clean panel, so things are operating perfectly fine. 0.5 means you're losing 50% of power output, etc. We can also use that and invert it to get the soiling loss ratio. It's a little more straightforward. It's 1 minus the soiling ratio, and you get this percentage. So at 20% soiling loss, that corresponds to a soiling ratio of 0.8. And then, of course, for these decentralized systems, reliability really matters. In this presentation, I'm going to be referring to the number of days the system produces enough energy above the threshold amount. And by that threshold, it's really driven by how much energy you need to make sure your vegetables are full. Okay. Throughout this thesis, I'll be attempting to answer these guiding questions. How much is the dust soiling impacting these PV systems? how much are the dust aerosols impacting these PV systems. And additionally, we're going to propose a novel mitigation method, shape-enhanced aerodynamic dust removal. We want to assess if it's going to be effective for PV systems in West Africa. To answer these questions, I'll be using environmental data and model development in order to assess the impacts. I'm going to be using several kinds of data sources, which I'll get into detail in the next slide. These are going to be combined with first principles physics-based models using information we get from literature in order to quantify these dust impacts on the power output of panels, as well as to assess this novel mitigation strategy. Going into detail about the data sets used in the study, we're going to be relying a lot on ground-based systems. These offer really high-quality reference-grade measurements that we can use to do things like calibrate satellites, for example. The problem is that within West Africa, there's not a lot of them. So we're going to make the use of them as we can, but we really need to supplement them with satellite-based and other kinds of data. Satellite allows us to get very intentional spatial resolution. Many times the data sets that we're using are actually assimilating a lot of observations from several different satellites. And this can sometimes give us improved accuracy. For example, we're going to be using the Washington University in St. Louis data set that I got from collaborators. Additionally, reanalysis data refers to data that is using a combination of ground-based and satellite-based, as well as models that they've developed in order to get these really great global spatial coverage, really nice temporal resolution data set that researchers love to use in order to assess earth science, ask and answer earth science questions. The issue with this one is that there can sometimes be limited accuracy. And you'll see that more later in this presentation. In particular, I'm going to be using MERA-2, which is one of the reanalysis data sets that NASA produces. All right. Throughout this study, I'm going to be looking at two major dust impacts. One are dust aerosols, which are going to absorb and scatter the sunlight, reducing the amount of sunlight that's going to actually reach the surface of the panels. And then dust soiling is going to further reduce the amount of sunlight that actually reaches the photovoltaic materials within the solar panel. And so taken together, we can quantify the total amount of dust impacts, which I will begin to do next. All right, let me take a drink. All right, let's answer these questions. Here we go. Okay, so I want to answer what the impact of the dust is on these solar panels. We do know that dust impacts have actually been estimated for around the world. So if we look at previous studies, like this one done with an MIT researcher, they quantified about 4 to 12% of aerosol losses are due to air pollution in these major cities that they looked at. In another study done in the Atacama Desert in Chile, they quantified that dust soiling, the dust that collects on the surface of panels, produce up to 40% of the energy annually in some desert regions. Additionally, another study using their MERA-2 data set quantified that more than 2/3 of the total dust production is actually due to dust soiling as opposed to dust aerosols. The problem is that we're not sure how well these measurements are going to apply to the global south. So for example, if you look at this other study done by Mitsu et al. 2021, you can see that what they did is they took these ground measurements and they interpolated it to get global coverage of estimates for quantifying the soiling by the soiling rate in percent per day. So how much additional loss do you get each day? What they quantified it by. You can see that these red dots are concentrated in the US, Europe, parts of the Middle East region, but not a lot in South America and not a lot in Africa. You can imagine that if you want to interpolate from these data sets, the accuracy for regions that we care about might not be the best. In order to overcome that, you can use these satellite and reanalysis-based data sets. And that's actually what researchers do. They use NASA MERA-2 to get estimates for dust impacts throughout the entire world. But the accuracy of these data sources is also questionable. So if we look at this figure to the right from colleagues at Washington University in St. Louis, these black circles represent the ground-based monitors that they use to calibrate the satellite data that they're going to be using for these studies. You can see, once again, concentrations in the US, in Europe, parts of South and East Asia. And you can imagine that this might lead to accuracy issues from these data sources outside of the global north. So we have to keep that in mind as we do our analysis. In particular, our objectives for the study are going to be quantifying dust impacts on PV power and reliability, quantifying the implications of these data limitations. We're going to relate these dust impacts into the design and operation of these decentralized systems in particular. And then finally, we want to determine pathways to mitigate these effects in the region. So, where do we begin? We're going to start by using these physics-based models. As I mentioned before, we're going to be taking these PM concentration and other environmental data sets, developing these physics-based models that tell us how much is going to collect on the surface of panels, relate the mass of the dust on the panels to the amount of power loss here. And that is better described in this pictorial image from Cologne World 2019, where we're going to assume some ambient concentration of particulates in the atmosphere. These are going to gravitationally settle onto the surface of the panels. Then, based on the amount of mass that's collected in the panels, we can estimate how much less power we're going to get out from the panels. We're also going to assume that when we get enough rain that passes a certain threshold, that is going to clean away the dust and allow us to restore our power production conditions. Solar ratio of 1, if you recall. We're also going to be comparing the data sets that we're using to ground-based data from the US EPA's AirNow network. This is a set of ground-based air pollution monitoring sensors that are established within the US embassies in major cities in West Africa. The benefit is that we get reference grade data. The downside is they're in major cities, so they don't necessarily represent the rural areas. Additionally, there's just not a lot of them. This is actually a huge amount of area. There's not a lot of monitors. We're going to do the best we got. The size of the circles represents the amount of data we get. A lot of these were also very recently installed, 2020, 2021. We don't have that much data or as much as we really like to have. But using these methods, we're able to begin to quantify these dust impacts. And that's what we're looking at on the left. So we're looking at our average, seasonally average soiling losses in the region. The DJF, MAM, JJA stands for December, January, February, March, April, May, and so on. These colors represent the degree of soiling, where blue means not very much, but yellow means a lot of soiling. And I'm going to draw your attention to this top here. This is December, January, February, right in the heart of the Harmattan season. You can see that a lot of parts of the region are experiencing quite a bit of soiling. As we get into March, April, May, this begins to recede as the rain belt comes in, as I described earlier. Until we get to the summer monsoon season, the rains have washed the dust away. We don't have as much soiling loss. You also can see this hot spot of yellow now in Chad. This is actually the Wesley depression, which is one of the largest sources of dust on the planet. It's known to carry dust all the way to the Amazon rainforest, for example. What we're going to do is focus in on Ilorin, which is a city in Nigeria, and we're going to begin to capture the amount of aerosols in the atmosphere using aerosol optical depth. I want to draw your attention to two things. But first, let's describe these colors. These represent the different data sets that I'm using to get the environmental data. Blue is ground-based. This is our ground-based truth. The orange represents the reanalysis data set, and the green represents the satellite-based. What I want to show you is that you can clearly see the Harmattan seasons here. You get these peaks at about the same time each year. What I also want to highlight is the magnitude of the AOD. We're looking at monthly averages of 1.2, 1.4. For reference, in the United States, the annual average is 0.2. So these are an order of magnitude higher. These are also monthly average data. When we talk about daily aerosol amounts, we can sometimes see AOD values above 3, which is really high. So the data sets can definitely impact how we design, how we assess these PV systems. So we're going to look at this chart to the right. This is a time series of 1 year on the x-axis and PM concentration on the y-axis. We're using the same data sets, the ground-based analysis and satellite. You can see that the blue is all the way up here in the Harmattan season, which I've highlighted in gray. Then you can see that the reanalysis and satellite data sets simply cannot estimate the highest amounts of PM concentrations in the region. So what we do is we're going to do a bias correction. A very simple one here. We're going to take this orange line, we're going to multiply it by 2 to get this red line. We're just literally multiplying by 2 to allow us to better capture the highest PM concentrations. And what this allows us to do is improve the accuracy of our model. So we see the results of this. It's the same x-axis of 1 year, but now we replace the y-axis with the soiling ratio. So once again, this is the degree of soiling. The further down you go, the more soil you have on the surface of your panels. And you can see that using the ground-based data sets, we're going to estimate a soiling ratio of 0.7. If we were to use MERIT-2, for example, the reanalysis data set, you're only estimating 0.8. And so we do get a benefit by doing the bias correction, but we're still underestimating these largest soiling ratios by 33 and 17% respectively when we use these remote sensing-based data sets. This has to do with the limitations that I mentioned earlier. This also applies to the aerosol amounts. So using MERIT-2, if you're going to, for example, design a system to work 95% of the time, and you use the MERIT-2 data to do that, you're going to undersize your system by up to 9% using the MERIT-2 data in this region. By doing the bias correction and by applying other methods in our model development to make improvements, we're able to make a 50% improvement in accuracy when compared to ground-based measurements of soiling and compared to literature models. So even though we're not capturing the full amount of the soiling, we're doing okay. And using this, we're going to move forward to make sure we can understand what exactly is happening in the region. So we're going to zoom in on Bamako, Mali, another part of West Africa. And what we're looking at here is the same y-axis, the soiling ratio, but now we've extended it to 20 years. I want to draw your attention to a couple of things. You can see that these lines, they're clearly going to have minimums during the Harmattan season, but they're not necessarily equidistant. This shows that there's intra-annual variation that we need to account for that many experiments have not yet accounted for. What I also want to do is we're going to use our model to now simulate a situation where we're going to be generating energy, but we're going to specify that we can't have more than 3% loss due to soiling. So anytime we begin to approach that number, we're going to clean the panels. And what we're going to do is begin to see some relationships here. So zooming in on 1 year and showing that here, same y-axis, but now it's just 1 year. And what we've done is we've shown these cleanings in the dark blue on the bottom. What this is showing us is two things. One, we're only going to clean during the Harmattan season. We're not going to clean during the monsoon season when the rains come. There's not as much dust. It's washing the dust off for us. Two, it's showing us how many times we need to clean it in order to get this particular amount of performance, no less than 3%, no more than 3% soiling loss. So we can begin to develop a relationship here. And that's what we did. We have this number of cleanings related to the average maximum soiling loss. And so where the number of cleanings is derived is included in this X term. The SO max and K terms are derived for each location based on 20 years of simulation. And this SL tells you how much soiling loss you can expect. So if I want to, for example, keep my solar panels below 3% soiling loss, I can go here, come across, see that I'm going to need to clean it at least 10 times, most likely during the Harmattan season, as I've shown to the right. And so we've derived those values of SO max and K for many major cities throughout West Africa so that users of decentralized systems can plan to operate these in a way that's going to meet their requirements. Right. Now we can come back to these study objectives. We can quantify dust impacts on power and reliability. Yes, dust soiling can cause more than 50% power loss in most affected areas. And as I showed in the paper, dust also reduces energy generation by up to 16 and 34% during the Harmattan season. Can we quantify the implications of regional data limitations? Yes, we showed that Montgomery 2 is going to underestimate the highest impacts in soiling by 33%, and you're going to underside your systems by up to 9%. We also can begin to relate these dust effects to the design operations of these decentralized PV systems. And what about mitigating? Well, we haven't actually done that yet, and so to do that, we're going to need to combine with the soiling aerosol models to really understand what's happening. Okay, so we're going to combine these models, and in particular, we're going to be comparing them to these AeroNet locations. AeroNet describes this NASA network of robots that are going to capture the amount of aerosols in the atmosphere in particular locations. I'm going to draw to a couple things. Chinzana, Ouagadougou, EMA are in the north, Landfill Station, Koforidua in the south, Jugu and Lauren are somewhere in between. And that's what orients us for this plot on the right, where I've mapped on each of these cities to their total dust impacts. We're looking at the amount of energy loss in the Harmattan season in West Africa, and we've broken it up by these different causes: dust soiling, natural aerosols that come from the Sahara Desert, and then these anthropogenic aerosols that come from human activities. And we can begin to see a few things. One, in places like EMA, very close to the Delhi Depression, you can get up to a 40% loss in energy production due to the dust impacts. Additionally, we can begin to see that in these northern locations, a lot of the impacts are actually coming from dust soiling. So we're going to take this chart, we're going to flip it so that it shows the relative contributions of each. So we're going to 100%. We would expect that all these going to 100%. This allows us to do is see very visually what the largest impacts are coming from. And we see that in these northern locations, it's mostly coming, over 60% is coming from dust soiling. However, we see these more southern locations that most of the impacts are actually from natural dust aerosols from the Sahara Desert. What this shows us is that most of the impacts of dust in these locations, you can't actually do much about it, right? Unless you can extract the dust out of the atmosphere, there's not much you can do about it. There's no need in the atmosphere. You're going to reduce energy. The best thing you can do is target this green, which is anthropogenic aerosols. That means that you can pass legislation to improve the air pollution and reduce those impacts on the solar panels. So that allows us to determine the pathways of mitigation. we know that depending on which area you're in, if you're in the north, where you're most affected by the dust, we need to target the dust soil. However, if you're further south, air pollution is going to be the biggest driver of the dust impacts for your particular location. This also allows us to answer our overall guiding questions that I asked in the very beginning. How much does the dust soil impact the PV systems? More than 50% power loss. How much do dust aerosols impact these systems? Let's see, it's going to give us reduced energy generation by up to 50% on the Harmattan, which I showed in the document. And then we now need to answer this: could shape-enhanced aerodynamic dust removal be an effective mitigation method? But I also want to highlight that these were presented and published. So we published our dust zone results in Applied Energy in 2023 and presented the dust aerosol results at the fall meeting of the AGU. All right, so now we need to get to this last and third question: could shape-enhanced aerodynamic dust removal be an effective mitigation method? Let's do it. So we're looking at ways to mitigate dust soiling because, as we've identified, the most affected areas are mostly affected by dust soiling. So we need to do something about it. There's lots of things you can do. As I mentioned before, you can try to target the air pollution. You can send people up to the panels to manually wash it. A lot of people have looked at robotic and other tech-assisted cleanings. For example, these electrostatic methods, as actually done down the hallway from researchers at MIT, where you basically create a voltage potential, charge the particles, and use that to remove them off the glass surface. There's other techniques like dew prevention, so you can invert the panels overnight to make sure that they don't collect dew, which helps collect dust. And then there's also passive techniques. One of the most popular is to do a coating, particularly a hydrophobic coating. That's going to change the way the water beads up on the surface and impact the way that it does collects onto the surface ultimately. These do have limitations. For example, these active cleaning techniques are often really expensive. You can't necessarily put the electrostatic device, especially not on these decentralized systems where you might have an entire street lined up with these solar powered telephone poles. It'll be a challenge. Additionally, these coatings are effective, but they do have limited effectiveness because they ultimately degrade over time. And additionally, they do not necessarily capture or reduce the dust effects for all sizes of dust, for example. Other methods also have some limitations. For example, the blocking the dust flow path, like trying to keep the dust from going in from the wind, does nothing to keep it from settling out of the atmosphere onto the surface. So here the literature gap is that these mitigation methods, we need mitigation methods for these decentralized PV systems operating in the global south in particular, and a passive dust removal method that is both durable and cost effective would really be ideal here. So to do that, we propose shape-enhanced aerodynamic dust removal, or SEADR, as we're calling it. And the idea is simply to adjust the model geometry to improve airflow. We have this conceptual artistic mock-up by an undergraduate in North Carolina, where they just applied the airfoil and put a solar panel on top of it so we can begin to think about ways that we can change the geometry to increase the airflow, for example, over the surface and ultimately remove more dust. This is the idea. And so the objectives of this particular study are to determine the feasibility of SEADR in West Africa, begin to quantify the potential benefit, and then finally identify and assess the performance of these panels. So to begin, I'll get into the fundamental physics. We're looking at the adhesion and removal physics of these particulates on the surface. I'm going to briefly describe this free body diagram. We have a particulate on a glass surface. There's a couple major forces, namely the van der Waals force and the capillary force, which refer to these atomistic forces that are going to keep these surfaces connected. And then additionally, the capillary force, which refers to the water that's going to form these bridges in the corners. They adhere to the surface. It's a really powerful force relative to the size of the particulate. We're going to imagine this incoming wind flow. This U star value refers to the amount of shear that's going to be acting on the surface in the viscous sublayer that the particulate sits in. And then there's a couple ways that we can remove the particulates, either via sliding, lift off, or rolling. Literature suggests that you're really just going to roll on the panel. All the other methods almost never happen realistically. So we're going to be identifying rolling. What we're going to do is we're going to quantify how much force is going to be imparted by this incoming wind. And using that, we can define this threshold so we can estimate when the particulate is going to roll off the surface of the panel. So by understanding the physics, we can begin to predict if it's going to roll off the panel based on the incoming wind flow. And so by doing this, we can begin to also highlight which parameters are driving our removal particulates, or in our case, really increasing the shear stress to apply the force to get it off of the surface. And we find that particulate particle diameter, shear velocity, and relative humidity are really strong drivers. The relative humidity is low enough, you don't get that capillary force. All right, let's continue. Literature shows us that when you have high winds, high wind speed, if you have low humidity conditions, you're able to get a net removal of dust by incoming wind. And lucky for us, in the Harmattan season in West Africa, right now we're looking at relative humidity in Ouagadougou, capital city of Burkina Faso. We're looking at a couple years of time. The y-axis here is relative humidity, and I've highlighted the Harmattan season in gray. You can see that during the Harmattan, we're at all-time lows in relative humidity, 20%. And according to literature, that suggests to us that we won't get that capillary force that we know strongly dictates if we stick to the surface. Additionally, we're almost doubling the amount of the wind speed, and this is based on Merit 2 data that we're using to create these plots. So during the Harmattan season, we're getting conditions that we find favorable for the wind removal of dust from the surface of the glass data. But we can further begin to support this with ground-based data. So for the past several years, I've been working with collaborators at Sheffield University to develop a monitoring network that we can install as a net, which is prepared by AeroNet. And it looks like this. This was recently installed just a few months ago. What we're doing is we're capturing the solar power production, dust mass that collects on it, as well as a plethora of environmental data, including wind speed, temperature, relative humidity, and irradiance. And so we're going to get all these measurements. And what this allows us to do for this study is begin to assess what kind of wind speed we can expect in this particular location. And we find that the wind speeds, in this case, between 10, 12.5, 15 meters per second, when we look at 3-minute intervals of Harmattan wind speeds in the area, suggests to us that, wow, things might actually be even better than what Merit 2 says, in terms of getting wind speeds to be able to kick up the dust from the surface of the panels. This development work in terms of getting the monitoring network up and going has also been discussed at conferences. We published an IEEE for initial prototype, and then we'll be discussing it in June in the IEEE Photovoltaic Specialist Conference coming up. So what we can do now is apply these physics models to understand if we were to arbitrarily increase the shear stress, what kind of results would that have in terms of decreasing the amount of mass on the surface of the panels? Mass is one of the driving variables that we use to capture the power output for the panels when we're doing dust-laden modeling. And we're going to be using Harmattan particle size data from literature. What we do is we apply those physics models. We're going to say we're going to arbitrarily increase the shear stress on the particulate, and then we're going to quantify the amount of additional mass removed relative to a reference case and see if we're able to increase the shear stress by a factor, what impact would that have? And so what you see here are different colored lines. These represent different wind speeds. You need a certain threshold wind speed to get any of the dust off. But as you begin to increase the wind speeds, they're going to eventually converge because the next smallest particle is going to require exponentially more wind speed in order to get off. Once you get very small, there's almost nothing you can do to get them off the surface. This is why PM2.5 is so bad for your health as well. Your body can't remove it. And so what we do is we see that a factor of 2 increase, for example, would get 91.3 additional additional mass relative to the reference panel. So if we're able to do a little bit of increase in shear stress by changing the shape, for example, it's going to have large results in decreasing the mass. Even if we can get 1.5, for example, that might still give us 50%. And so if we apply that to our dust-laden model with 50% less mass collecting on the surface of the panels, we can see that we can reduce the highest amounts of soil ratio, in this case in the lower end, by quite a bit. So this allows us to begin to answer some of the key objectives. What is the feasibility of SEADR? Well, we see that given the uniquely high wind speeds and uniquely low relative humidities in this particular part of the world, these are really conducive conditions for getting the particles off the surface by using wind. Additionally, we can begin to quantify the benefit of SEADR, which we see in the previous chart, removes 50% more dust mass. Removing 50% more dust mass would reduce on average the soil ratio by 30%, 36% in the lower end of this example. The final step is now to identify and assess the performance of these SEADR shapes and SEADR panels. So we're also going to do that. Let's do it. We're going to start simple. We're going to explore 3 Very simple shape. We're going to start with the flat plate. We're going to bend the flat plate so we can get this arch shape. And then we can also cut the corners off of the flat plate in order to make it more streamlined and get this ellipse shape. We're going to be adjusting a number of geometric parameters to see how those relate to the shear stress over the surface. In particular, I want to draw your attention to the tilt angle and azimuth. Tilt angle refers to the angle the panel is making relative to the horizontal surface, right? So this is the angle in this direction. The azimuth angle represents the angle that you're making relative to the cardinal coordinates. So in this example, you're facing south. If you're in the northern hemisphere, you typically want to face south to get the highest amount of energy. We're going to come back to this slide later. We're also going to define a reference case of about 100 watts in power output. So it's 1 meter in length, and the width is 5% of the length of it at 0.5 meters. That'll be our reference case when we're comparing the shear stress. So we're going to be integrating all the models that we've developed to this point in order to assess the impacts of the SEADR shapes onto dust smoothing impacts. And so we're going to start with this aerosol impact model, which really is a radiative transfer model to estimate how the different angles are going to correspond with how much energy you get onto the photovoltaic surface. We have this dust shielding impact model that translates the PM concentrations into the amount that collects in the panels and the power output. And then we're combining it with those fundamental physics models that we talked about a few slides ago. And on top of that, we're going to be adding some ANSYS fluid computational fluid dynamics model developed by very own Chelsea, who's also in our in the Asia Road Lab. What this is a two-dimensional Reynolds average Navier Stokes simulation. And all that means is that we're going to be using some very powerful technology in order to estimate the amount of shear stress along the surface of the panel, as well as other flow conditions around the geometric shapes. You can see an example here. We're looking at the velocities as it flows into a very thick panel and angle. So we also need to begin to understand the limits of things we can do for these geometries. And so we're going to first begin this by mapping the design space and identifying those limits. The way this works is that we have some parameters that we can change. We need to compare, we're going to compare an unsoiled SEADR intervention with a more conventional panel that does collect dust. What does that mean? This is going to be our comparison point. We have this panel, it's collecting dust, it's conventional. We want to make sure that anything we do to the panel is going to outperform this in terms of generating energy. So we're going to be looking at a 3-year simulation of generating energy using the SEADR panel versus this dust soiling panel. And we're going to be quantifying the improvement in terms of how much more energy you get from using the SEADR panel that is completely soil-free. So we're going to assume that SEADR works perfectly, no dust collects on it. We're going to compare it to this. We want to make sure that it's going to be worth it. So to doing that, we get charts like this. This is the total energy generated during the Harmattan season over this 3-year simulation. We have this baseline panel with no soil. This orange case that represents this one is collected soil. And in this green case, we're going to have, in this case, a curved surface operating in Niger. And we want to make sure that this green bar is ahead of this orange bar. This means we have a positive improvement. So this is how we can define the limits of curvature in this case. We're going to apply this to a lot of these other geometric parameters like tilt angle. We get plots like this. So on the x-axis are the tilt angle, and we're increasing it as we go to the right. We have an improvement here where this cutoff line is at 0. That means anything below this line is no longer worth it. For a given solar panel in a given location, there's usually an optimal tilt angle that you can pick. And so you can see that in Niger, it's around 15 in this case, where we're getting the peak in improvement in terms of comparing our tilted panel to a flat panel that has lots of like dust. Once we begin to tilt it beyond this point, we're going to get less and less improvement until we hit this cutoff point around 46 degrees in terms of the tilt angle. Anything beyond that is no longer worth it. We tilt it beyond that, even if we could remove all the dust, it's not going to be worth it because you're generating so much less energy. It's not worth making that change. So when we do that, we're able to define the geometric limits that we'll be exploring in terms of these SEADR shapes. So I compute the range of tilt angles, azimuth angles, and curvature so we can account for. Curvature ratio just refers to the amount of bending that we can have. The deeper the curve, the lower this number. At a curvature ratio of 2, it's a full circle. 15 is more like a flat plate. I choose the wind speeds based on the environmental data of the region, and then I arbitrarily chose this at 20% because it's pretty thick relative to what we normally see commercially. These widths are determined based on commercial values, commercially available panels that I can find at 100 watts and 250 watts in terms of the power output. So we're going to be exploring these limits. We want to see some trends in terms of how we change these things, how that impacts the shear stress, and ultimately the additional dust removed from the surface of a panel. There we go. Okay. We're going to be looking at this chart here, and ultimately we want to find that arc to the best performing shape of those very simple shapes that we started with in the beginning. So once again, we have tilt angle on the x-axis, additional mass of dust removed relative to our reference. We're going to start at this blue line. This is going to represent a flat panel that is tilted at an angle, in this case with a 20-degree thickness, and we see a few trends. One, very straightforward one, the shorter you go, the more average shear stress you get over the surface. That's because you're going to dissipate less energy as the wind blows over the surface. Additionally, by making changes like tilting it at an angle and making it thicker, you're going to change what's known as the stagnation region, essentially where the stagnation zone is essentially where the air comes to a stop and needs to reassess before it can move around the rest of the surface. By changing that location, you can increase the average shear stress over the surface. So that's for the blue one. For the orange one, this is the elliptical shape. You can see we get something a little better. It's more streamlined. We're going to be accelerating the flow over the surface. And then once we move to, well, I guess rethinking about that, generally as we increase the curvature, we want to increase the shear. Because we want to get more flow acceleration over the surface. But this also depends on the wind speed and the length or the Reynolds number. So depending on which Reynolds number you're at, is going to also dictate what maximum curvature you can do that's going to increase the average shear stress. In this case, at 10 meters per second at 1 meter in width, we're talking about a curvature ratio of 4. We'll also look at the elliptical case. Essentially, what you're doing is you're decreasing the size of the stagnation zone in order to get slightly better results in terms of the average shear stress over the surface. And so this is the best performing shape that we evaluated in terms of the simple shapes. And looking at the amount of additional dust removed, you can see we can get up to 67% additional dust removed, whereas with the modified flat plate, thickening it, shortening it, tilting it at an angle, you get up to 41% reduction in terms of the additional mass. All right. Yes, removing mass is a very good thing. That's ultimately what we're aiming for. But really what we're aiming for is improving the energy generation in the region. So to assess these shapes, we need to estimate how much energy we're going to generate. We're going to pick Niamey because it's one of the dustiest places in the region. And we're going to simulate 3 years of energy generation based on the dominant Harmattan plants. So on the right axis, on the right side, we're looking at a figure of a windrows where the direction represents the direction that the wind is coming from. The wind is blowing from the northeast in this case. And these different colors correspond to the different wind speeds. Those don't matter as much for now. What I want to focus on is the direction. This is for annually. We're going to switch it to be Harmattan season only. We can see that we're getting that ICCC, bringing the winds in from the northeast region. And so in order to get the benefit of those winds, we want to assume we're going to face that for now. So between 22 and 45 degrees. We're also going to consider 4 reference cases. A reference flat plate that is sitting flat to the ground. These are known to collect a lot of dust. An optimally tilted flat plate when it comes to generating energy. Then we're also going to do some SEADR adjustments. We're going to take that flat plate, we're going to thicken it, we're going to change it to the angle where we find the greatest increase in average shear stress over the surface. And then finally, this arc shape that we found was able to increase the amount of dust removal. I want to bring back the reliability term that we mentioned before. It's going to come up again. And essentially, this is when panels produce energy above the threshold amount. So we're evaluating how well these shapes do when it comes to generating energy and removing dust. We're going to start by looking at this familiar chart on the left. And we see that for this given 3-year time span, looking at the different soiling ratios of our 4 different reference cases, we see a couple things. One, these flat plates with no SEADR interventions are getting the highest soiling ratios, 0.6, 0.75, etc., depending on what year you're in. Once you start to make these changes, you're going to reduce the amount of soiling that happens on the panel. Specifically, if you're able to use the arc panel, you're going to reduce the maximum soil loss by 46% in this case. And this is in Yemen, Niger. When we also consider the energy generated, we do see some benefits. So these are allowed to collect dust. They are optimally tilted and oriented, but they're still collecting dust, and so you're not going to get as much power output as you'd expect. Once you tilt it, you're going to get less gravitational settling, and so you're going to reduce the amount of dust impacts. By switching your panel to face the wind, you're going to significantly reduce the amount of energy generated. So even though the flat panel isn't collecting as much dust, it's not collecting as much energy. And in this case, the arc panel is able to produce more energy than a optimally tilted panel that is allowed to just collect dust. But this is not always the case. So this is looking at Niamey, Niger. We switch to, for example, Chinzana, which is in Mali, another desert area, also part of the northern region of West Africa. You can see that actually the arc panel does not generate more energy than the optimally tilted panel. That is literally just collecting dust. So, does that mean here can still make sense? Well, potentially yes. What we're looking at now is the distribution of daily energy generated. You see that on the x-axis, where the density just represents how often you would expect it to generate that particular value. And what you see here in all locations is that this arc panel is going to be generating higher values, is more likely to generate higher values than less likely to generate smaller values. And that's because you're not getting as much loss with the depth of the Harmattan. You're really increasing the amount of dust going to the surface of the panels. So we find that this is going to increase reliability at the 96th percentile by 30%. So this allows us to answer our last objective. Let's identify and assess the performance of SEADR panels. It's going to potentially remove up to 67% more dust mass than conventional panels, and you can improve the reliability by 30%. That is particularly important for things like the vegetable cooler. We need to make sure that your vegetables stay cool, they don't spoil in your particular climate. This also allows us to answer our final guiding question: could Shape-Enhanced Aerodynamic Dust Removal be effective? Yes, these SEADR shapes can potentially remove more dust and increase reliability. And as last time, this has also been presented where we presented on the SEADR results at the APSDD conference in October. So this allows us to actually jump to the acknowledgements. I'm gonna do those first because I want to make sure I can have a chance to wipe my tears before we actually get to the questions. So let's do it. So first, I want to thank my funding sources. I want to thank the Hugh Hampton Young Fellowship, the Martin Fellow, the NASA JPL CERP, which funded the really the initial effort into this project. Missy Africa, which has sent me to the continent, the Archie Cornfield Teaching Fellowship, which also took me to the continent, as well as the PKG Social Impact Fellowship, which took me to the continent last Saturday. This is an image when I was working at Ashesi University as a lecturer. I also want to thank my colleagues, collaborators, and mentors. I want to begin by thanking my committee members, Dr. Andrew Biggis and Olga Kashikova. I really appreciate you all being on the call. As you don't know, they're in California and Perth, Australia, so it's quite early and quite late to go with them. So I really appreciate all of those efforts. Olga, especially, thank you for really taking the chance and funding this research project. I'm really grateful. Professor Henry, I want to thank you as well for continuing to encourage me to do as best as I can and continue to improve the quality of the research. Professor Wood, thank you. You're an existence proof that work like this is possible. So I'm really grateful for you and thank you for supporting my journey. Professor Harris, thank you so much. You've been there since the beginning. When I first went to Burkina Faso, I needed a faculty member to sign off. Professor Harris signed off. When I needed, I was trying to think through whether or not I should go to Ghana and live there. Professor Harris said, you should satisfy your soul. And I feel like I really cherish that kind of advice. These people have really been there with me since literally the very beginning all the way up to the end. So I really appreciate you. Thank you. I want to thank Dr. Gina Montague, who really kicked this all off by reaching out and having some undergraduate students work on the solar power incubator. It's completely changed my life. I want to thank Dr. Heather Bean, who encouraged me to come to Ashesi University, has mentored me at Ashesi, and continues to be an incredible collaborator. I want to thank Michael Gray, who's also part of the JPL team, working with Olga. You've been a great support, and I've learned quite a bit from you. Thank you so much. Aaron Von Donkler, Melanie Hammer, Hugh Lee, these are collaborators I've worked with, as well as students I've worked on research with, including Kimpira, Francis, and Jeremiah. Thank you all so much, especially from the fall right now. I also want to thank more colleagues, collaborators, and mentors. I want to thank Dean Staten. Thank you so much for all of your advice. Dean Creighton, thank you so much, especially advising me through a really tough time. Ari, thank you for your funding and support with Missy Africa. I originally started my journey in the laboratory for aviation environment. Thank you to the LAE colleagues who joined me today. I've learned so much from you all in terms of how to present, how to do research, how to be thorough. We've also just had a good time. And in particular, thank you to Stephen Barrett for encouraging my research and also admitting me to MIT as well. I want to thank the MIT Lab for giving me opportunities to not only do cool projects, but also to teach and learn quite a bit in a really nice community. The OGE staff, the aerosols staff, thank you so much for being here and helping me throughout this entire time. I want to take time to thank Norma, also as part of the aerosols staff, and there's a very important function that wouldn't allow us to run this, to operate this school without her. I want to thank my undergraduate student researchers, especially from Nepal, if you're here today. Thank you so much, Serena, Obadele, Andre, Xavier. You all really helped me in terms of increasing my understanding of the project and also advancing some really cool stuff moving forward. I want to thank my other undergraduates that advised, Nesha, Kampira, and Sahafi. Thank you all so much for doing for my journey. Continuing. I want to thank the media communities that I've been a part of, the media communities I've been a part of here at MIT, the Academy for British Minority Engineers, Aero Afro. Actually, when I got here, Aero Afro did not exist. We really put a lot of effort to make sure it existed, and since then, it's really blossomed and had a large impact on campus and really the entire MIT community. So, in particular, thank you, Dr. Arthur Brown, that supported front end. You all were instrumental in making sure this could happen. I want to thank the Baker House community. I've been looking at Baker House for the better part of the last 6 years. And so it's been a really important living space for me. It's been a really great opportunity to mentor, work with other people. I want to thank the MIT Gymnastics Club. Thank you all so much for giving me an outlet and being able to be a part of the team as I work on my physical health and abilities. Thank you to the Black Alumni of MIT, Black Student Union, and also Minority Education. You all fantastic communities. I'm really grateful for you all, especially if you're here today. Thank you so much. Continuing, I want to especially thank the Black Graduate Student Association. I think also when I got here, the BPSA was not active. And so we took a lot of effort to bring it back. And since then, it's really blossomed into a beloved community. I'm so grateful to be a part of it. I've learned so much by serving this community. I've grown my leadership. I've grown my ability to be a good friend. I've had a lot of great opportunities, and I've been just marveling at the impact that we've had on campus in the last 6-7 years that we've been working on this. So in particular, I want to thank you to that original E-board team that really brought it back from the ashes and made it what it is today. I want to thank the last E-board team for really holding it down in a really interesting time and continuing to live with, really pushing me to be the best I can be and live with, I'm losing my words right now, but fantastically, I suppose. I want to thank my good friends. Thank you so much to everyone listening here. Ledger, Arthur, Aisha, Ashley, Bayon, Cadence, Chelsea, Curtis, Jackson, Kevin, Michael, Miles, Wilson, Paul, to the Trevor, Spawn, and Wills. Y'all have really helped me down since I've been here. Some of these people on this list have literally been there since day one. They helped me do CV 100. They've helped me every time I had a fellowship. Here we go. Every time I had a fellowship application due, they're the ones that edit it. Every time I had to prepare a presentation, you're the ones support me in terms of putting in the hours behind the scenes to make sure things like this can go very smoothly. Whenever I need a chance to just get away from MIT and remember that life is more than just work, life is more than just accomplishments. There's more to life than that. These are the people that really held it down and helped me get through that. So to you all, you are incredibly valued and important to me. Thank you so much. And then finally, I want to thank my family. Thank you all for being here. It's a very special day for me, so I'm grateful that we could be here. Thank you all for instilling in me the values and the actually research skills from being curious and exploring and moving the world with confidence, and also Montessori education, which has been invaluable for me today. So, with that, we now get to the conclusions. We'll end this. Let's do it. All right. So the original research question: could dust be having a significant impact? I saw that my panels were working. I wanted to assess: is it the dust that could be having an impact? My hypothesis was that yes, I think it could. It could be significant, but I think there's something that we can do about it to make things better. I have my guiding question: dust solely causes more than 50% power loss in most affected areas. In order to answer this first guiding question of whether the dust solely impacts. My second question: how much of the dust aerosols impact these systems? Both can reduce energy generation by up to 50% during the Harmattan season. And then finally, could SEADR be the effective mitigation method for PV systems in the region? Well, we think that it could remove up to 67% more additional mass just by bending it and potentially improve the reliability by 30%. We did not only answer these guiding questions, but in the process, we really added significantly to the field. In particular, we've improved the dust impact quantification in the region. So, we developed these environmental modeling techniques that can account for these remote sensing limitations to do things like improve the modeling by 50% in terms of accuracy when compared to existing models. We were also able to develop metrics that allow us to assess these dust losses that are particularly suitable for these decentralized systems, which we know are going to be very important, as opposed to only conventional PV, like the swelling percentage per day. We also quantified the relative impact of these anthropogenic and natural drivers, which allows us to identify geographically specific opportunities for effective mitigation strategies. It's not just let's improve the air pollution. It's not just let's use these robots to clean it. It's I'm located in Lamto Station. I need to use air pollution, or I need to look at something that can remove the dust soiling in Yemeni share, for example. We also expanded strategies for improving solar panel performance in the region and elsewhere. Well, we proposed a novel method for passive soiling mitigation, which is SEADR. We developed techniques for assessing these shapes, and we identified important trends in terms of how we adjust the geometric parameters to increase the shear stress. This is really the foundation for what we can do next, which is now look at non-simple shapes, more advanced shapes. Using the trends that we learned, we can begin to parameterize these shapes and understand what real SEADR shapes look like that are good in the trade-off between dust impacts and energy generation. We also identified solar panel aerodynamics as an important design consideration when we're designing these panels to improve the performance. This means that, for example, not only is increasing shear stress expected to increase the dust removal, as you might know, increasing shear stress is expected to increase convective cooling as well. And since panels are very sensitive to their temperature, increasing the cooling could allow us to have more efficient panels potentially. Additionally, solar panel aerodynamics are an important consideration when designing experiments, since a lot of times people are looking at ways to assess the soil length without looking at their panel aerodynamics, which we know could have a significant impact. I also want to make sure we know that this work has wide applicability. On the left chart is a chart of PV power potential from solar GIS. The way to read this is that the deeper the red, the more expected PV power output you can get from the panels. So you can look at places like Atacama, places like Namib. These are all desert regions as well. And so you can expect that where there's PV power, you're probably also in the desert. And when you're in the desert, there's probably also dust. So the methods we've developed today can be applied to these other regions that might also suffer from not having very accurate data. They can be used and applied to make sure you understand what the dust impact is going to be in your particular location. It's also not just applicable to Earth. We also have applications on Mars as well. We're looking at the InSight lander here. This is an image when it first landed. This is an image a couple years later. It's emitted dust. What's known in the Martian rover and lander design community is that oftentimes the dust collection is a limiting factor in terms of how long your mission can last. We also know in the Martian community that the high wind conditions, the very dry conditions, can sometimes lead to dust removal from the surface of the panels, which we also know can extend the lifetime of panels of these rovers and landers, as it did for Curiosity and the other rover as well. So we can apply this to places off the planet, not only just on Earth. I do want us to come back to this initial picture that I took in Burkina Faso. One of the things that I didn't mention is that the reason it collects dust because a foreign NGO installed the system behind the hospital, hoping that it would help people. And what happened is the installations broke. No one locally knew how to fix it, and the NGO was given a return to fix it. It collects dust because it's broken. It does not work. One of the major themes of the work that I've done is that technology often designed in the global north, when applied to these regions, often perform poorly or unexpected. And we saw this in the data sets where we tried to apply the data sets that we're using, calibrated on global north data, they weren't very accurate. I saw this when I worked on the incubator project. The incubator systems actually didn't work very well because they assumed very different environmental conditions. The solar panels could be the same way too, where if we change the shape, for example, we can improve the dust mitigation impacts, but there's other things we need to address as well. PV systems operating in the region have higher degradation rates, battery performance is much worse, and overall they have lower conversion efficiency. So it's not just the shapes, we need to rethink the entire PV system, the installation, the design objective, the materials. We can begin to rethink all that to make sure that it meets the particular needs of the region. And in particular, we need local people to make sure that at the forefront of that as well. what we saw with the incubator project is that the way we brought it to an end was actually collecting the expertise of different people in the region, experts in PV incubation, experts in electronics, experts in solar panel, in order to get to our final solution, a locally designed solar-powered chicken egg incubator that can be built and used in Burkina Faso to meet their needs. People need to be within the design and other technology processes in order to get energy technologies that can directly meet their needs. This is something we're continuing to work on. I'm continuing to work with Dr. Gina Montague, where we actually are developing solar assembly capability in Tamale. That initial picture I showed you that collected dust was actually a locally assembled solar panel. What this is doing is creating the technical foundation within the community so they can begin to innovate in order to produce energy technologies that will better provide for their own needs. I often want to take a quick step back and think about how we got to this position in the first place, where less than 16% of the rural population had access to electricity in Burkina Faso. This gets us back to the thing that Professor Harris mentioned earlier, which is about two things I want to mention here. One is you can see that these are all near the Bedeli Depression in Chad. So these are very clearly areas that are going to impact and be important for my work. We're looking at dust impacts on solar panels. These are also oftentimes over French colonies. One of the reasons that we have the dire situation in terms of energy access is because these countries are still living in the vestiges of colonial extraction, or sometimes the presence of colonial extraction. And these communities struggle to produce their own energy technologies because of the way that global power is distributed. They didn't have the resources to be able to, the resources, both technical and capital, to be able to produce the energy technologies that they needed. And so, even though I've been working really hard, I really care about this problem, I think I have innovated in a way that I want to support people in the region. I know that the technical application of my work is only part of the solution. It's not the true solution. To really address it, we need to do something about this as well. So, with that, I'm now open to take questions. Thank you.